Hello, welcome to the doubts and problem discussion session for week 6 of the course content. This problem solving session is for the course of Strength of Materials taught by Professor K. Ramesh, and I am Abhinav Chandrakar, the TA for this course, along with Miss Archita Gogoi, who is the second TA. So today, as usual, I'll be covering uh, some summarization of week 6 contents, which will be followed by some doubts which some of the participants can ask, and then a discussion on the assignments of the relevant concepts. Let's wait for 2-3 minutes before starting. Also, in this session, I'll only be covering 2 of the 3 lectures which were covered in week 6. So that will be the first one, which was on um, stress and strain relationship, and the next one, which was interdependence between elastic constants. The third lecture will be taken by Archita, which is on thermal strains. I think hi Krishnakant, how are you?
I'm good.
Mhm. So I was just waiting that someone should join, then it's better to start. uh, okay, my voice is clear. You can hear me. Okay. So Krishnakant, this time also I will be taking some portion of week 6 content, and the more mathematical parts Archita will be taking. So majorly the first lecture, which is on stress strain relationship, and most of the second lecture. which is on interdependence of stress of elastic constants. So these two I'll be covering the concepts and the assignment questions. Archita will be majorly covering the whole of thermal strains. So we'll do it that way. And so were you able to go through the video lectures?
Yes, it's done. And actually, I wanted to complete assignment within 6 o'clock, but it is only quarter done.
Okay, okay, okay. Yeah. I think if you have seen the video lectures, assignments are not so difficult. You can quickly go through them. The lectures are more time taking, slightly. Okay, so let's just, I'll quickly, I'll not take much time. I'll quickly summarize. Then, if you have some doubts or something you want to discuss, we can look at that. Ah. So, these are some points I had noted down, which I felt were important. So, firstly, that most of the calculations which we are doing or the derivations which we are doing are on the assumption that we are considering only small deformation. So most of them are only applicable for linear elasticity. But these simplifications are also many a times applicable for real life scenarios, for example, in fatigue. So many a times it's okay to make such simplifications. Then we have certain techniques called whole field techniques in which we can measure the variation in the uh, at various points simultaneously. For example, when measuring strains. So such kinds of techniques are called whole field techniques. So you can also get the directional value of what you're measuring, as well as at different points you can measure it. Then there is something called constitutive relation, and um, I'm not sure of the exact definition of it, but it's a relationship between different entities. For example, a relationship that you write between stress and strain, which is a theoretically developed relationship. It is called a constitutive relation. We'll see what that relationship is in the next few points. If you have any questions related to any of these from the video lectures, you can ask me. Then we have in the lecture, sir has categorized the deformation behavior of different materials into some different buckets. Like you can have rigid materials which do not deform, then plastic materials which are 100% plastic, so they will deform without any requirement of higher stresses. We can have linear elastic, which show linear stress strain dependence. Then bilinear elastic, two different slopes in their graph. Then it can be elastic followed by perfectly plastic, elastic plastic, which involves some strain hardening. So these are just some categorization, simplification of a kind for doing modeling or for using these assumptions for further modeling of materials. Mhm. Then we'll see the concept of mu, the Poisson's ratio, and this is the definition of it. That sorry. So this is the definition of it. It's negative of the strain in axial direction by sorry. It should be the strain in the. It depends on how you load it. If it's along y, then it's negative of strain in x by strain in y. And it will be used a lot to form relations between stresses and strains. Then we have certain standards for measuring them, just like we had standards which were discussed when covering strain gauges. Some bodies are there which come up with standards. Similarly, we also have for measurement of Poisson's ratio. Then briefly, sir covered about true stresses and true strains, which are somewhat different from the engineering stress and the strains we were dealing with till now. So these are more like instantaneous values. So d epsilon 2 will be dl by L, where L is the instantaneous length. Similarly, you will take the area in your sigma expression, which is the instantaneous area of your material, cross section area. Then, sir, actually stressed on this thing that if you are applying uniaxial stress on any material, then you should not assume that the strain also will be uniaxial, because due to Poisson's ratio, it will have some strain in the other directions also. So the strain will generally be triaxial. And as I said, we make the assumption of small deformation in many of these cases, which assumes that we have a linear stress strain dependence. And it is true if if the strains you are looking at are small. Then we looked at how alignment of fibers or grains can lead to anisotropy in behavior, and that can later lead to differences in the stress strain relationship. So if you want to model such kind of materials, you have to take into account how the relationships between stresses and strains will change, because the elastic constants will change. So all of those things will have to be taken into account. I think Krishnakant, you are some noise is coming from your mic. Can you check?
No, sir. Might be construction going on here to the neighboring
Uh,
house.
Maybe just mute it if you are not speaking. Otherwise, in the recording also, this will come up noise. If you have any doubts, even small things you might want to discuss, you can let me know. Then after that, one very important property of isotropic materials was discussed, that if you are applying a shear stress on an isotropic material, then you will get shear strain only, which will be pure shear strain, and no normal components will be there. And same goes for normal stress also, and vice versa. If you are applying, let's say, a normal strain, then you'd only get normal stresses, no shear components will be there. So this makes dealing with isotropic materials very easy, since um you can kind of how do I put it, delineate the effects of shear and normal, because they have a one-to-one corresponding lens kind of. But if you have some anisotropic or orthotropic material, this might not be possible. So visualization also will be difficult of how stresses are leading to strains. Then we looked at, based on how Poisson's ratio was defined, we can also look at how strain will be affected by stresses applied in different directions. So even stresses applied in y and z direction will affect the strains in x direction, since strain will be triaxial. So epsilon x can be written in this manner, and the shear strain can be written in this manner. Since this is isotropic, the shear stress only will have an effect on the shear strain. Normal stresses will be separate. and this is called generalized Hooke's law. We'll see a more general form of this later when we look at the matrix form. And sir explained how we can derive the value of shear modulus and its relationship of shear modulus to the elastic modulus, Young's modulus, and the Poisson's ratio by looking at some simple cases. So it comes out to be E by 2 into 1 plus mu. Then the derivation for calculation of volumetric strain was covered. So volumetric strain is delta V by V, changing in volume upon loading divided by the original volume. And if you consider small deformation and so if you consider small deformation, you can remove many of the terms which will come in the more exact expression for this, and then you can just you will just have these three strains in the final term: epsilon 1 plus epsilon 2 plus epsilon 3. And if it is a hydrostatic kind of stress, since okay, so let's just say if the stress is hydrostatic, then you will have all the values of strains same in all three directions. It will be 3 epsilon xx, and this can then be written as T by E sigma into 1 minus 2 mu if you want to write in terms of stresses. Also, the reason we can consider this as 3 epsilon xx is because only the hydrostatic stresses lead to volume change. The deviatoric stresses will not lead to volume change. So another way of understanding this is that only normal stresses can cause volume change. Shear stresses will change your shape, but or shear strains will be causing a shape change, but it will not lead to a change in the volume of your material. And bulk modulus is also related to volume change. It tells you the ratio of the stress applied to the change in the relative volume. It is written as K. And this relationship was also explained by Sir in his derivation. Then we look at plastic deformation. So plastic deformation uh, so hmm, in plastic deformation we observe that there is no uh, change in the volume of a material. I'm not sure if you know the reasoning for it. Krishnakant, you are aware of it? Why we say so? You're not aware. Okay.
No, sir.
Hmm. So at least in metals, I can tell you that plastic deformation always involves breaking of bonds in a material. In case of metals, at least, or metallic alloys. While in elastic deformation, you will have stretching of bonds, right? So since plastic deformation is basically breaking of some bonds and then joining of some other bonds, making of new bonds through which the deformation is happening, there is no stretching of bonds per se which is taking place. So that is the reason it is said that if a material is deforming plastically, then it will not cause any change in the volume. It makes sense.
Sir, if the bonds are being broken, which means the necking is starting to happen, right?
Yes,
And
necking
then
is starting to happen.
we are seeing strain hardening case also, which is also plasticity.
Yeah, that is also plasticity. Hmm.
There, the necking will not start happening.
There the see necking will start after your we call it
MTS.
instability point, we say. I'll just maybe show it through a notepad. So when if you look at any typical stress strain curve, then or I'll just do it here. That's better. So you understand the point of instability. I think sir did not call it that, like mention this term in his videos. But what I mean is the ultimate tensile strength point, after which you will start seeing the necking. Yeah, I can. Mhm. So the thing is, even before that, you have strain hardening, right? And that is also associated with plasticity. So how you can understand this concept is that, let's say you were at this point, strain hardening started at after yield point. Let's say this is the yield point. Let's call this ys maybe. And here, if you just unload your material, it will come back like this. It will elastically relax, and some plastic deformation will be remaining, right? So this is the plastic deformation. And what we say is that this plastic deformation happened because some bonds inside the material broke, and there was some rearrangement in the atomic structures or atomic bonds, which led to the change in shape that we will observe due to the plastic deformation. But because it's just a rearrangement that is taking place, you do not have any stretching of bonds because it has elastically relaxed. So after relaxation, there should not be any change in the volume of the material. So I hope it made sense.
Little bits.
Okay. So let me just break it down. Once more, I'll explain. So let's say you are loading a material. So you applied a load. It initially it only elastically deformed. So the bonds got stretched, right? No bonds were breaking. So as it was elastically deformed, bonds got stretched, then you had some Poisson's ratio, according to which your material deform like had strains in the axial direction, transverse directions. But that also involved some change in volume. When you are elastically deforming, most of the time there will be a change in volume, and it will correspond to what is your Poisson's ratio. But once it will keep elastically deforming, but once plastic deformation starts occurring, let's say around this yield point, then what happens is that slowly the maybe already some dislocations or defects are there in your material. Then at those points some bonds will start to break, then new bonds will start to form in such a way that your material will deform in the direction in which you are applying the stress. So there will be a change in shape. For example, let's say the tensile samples you see, they starts to get elongated, right? As they plastically deform. So what is essentially happening is that the bonds are rearranging in that material. Okay, some defects are also getting created, or those which are were already there, they are getting propagated a bit. But essentially bonds are rearranging. So that does not involve any stretching of bonds, because stretching of bonds means there is an increase in the energy in the material. So after you relax, they will have to elastically come back to their equilibrium spacing. So bonds will come back to their equilibrium length. The energy will be same as what it was initially, but the volume, but the shape of the material has changed. Maybe you can understand that your tensile specimen has elongated, right? So that elongation is due to plastic deformation, and we say that this will not be associated with any volume change, because it has only the atoms have only rearranged. the atomic bonds have rearranged. So that is why we say that for plastic deformation, you have a Poisson's ratio value of 0.5, because this is associated with delta V equal to 0, right? And the reason this is so is because delta V by V is equal to epsilon 1 plus epsilon 2 plus epsilon 3, while epsilon 2 will become minus of 0.5 epsilon 1, right? If mu is equal to 0.5. Similarly, this will also become minus of 0.5 into epsilon 1. So this will come out to be 0. So that's the simple like explanation for it. Now, I think most things we have covered. For metals, it's usually about 0.3 when it is elastically deforming. For plastic, it's of course 0.5 only. And also mu will have a value of between -1 and 0.5 based on some theoretical constraints. So this was explained by sir. What is the reason for this? Also, for isotropic materials, among these four constants, only two of them are required to know about the elastic properties of the material. If you have any two, you can find the others because they are all interrelated. So these four are your Young's modulus, then shear modulus, Poisson's ratio, and bulk modulus. Now we come to elasticity matrix. So this is the matrix which relates the stress tensor to the strain tensor. Both stress and strain are tensors of rank 2, and the matrix that relates it is a tensor of rank 4. So I don't know how much you know tensors, but there is this kind of, according to the mathematics, if you have two tensors of let's say rank 2 and rank 4, then the tensor which will be relating both of them will always be of the rank equal to 2 plus 2 equal to 4. So that is why its elasticity matrix is of rank 4. That's all I'll cover about the elasticity matrix here. Then plasticity, sir told that the history of loading is very important when it comes to plasticity, and the reason for is somewhat the same as what I was discussing when I was telling about the change in volume involved in a plastic deformation, because when you load it and the material has deformed plastically, the microstructure or the internal structure of the material has changed, in the sense that now your material will have some other defects in it. So that will lead to a change in the properties of that material. And that is why sir had told that history of loading is very important. Since this course does not cover in detail about the defects in a material which govern the plastic deformation of the material or the processes involved in plastic deformation, so we need not look in more detail about this, but this is important. Then he also just mentioned about forging and how such processes can lead to change in your grain flow in case of metals. So this is also related to this thing only, history of loading. And at the end, sir told a more general relationship between stresses and the stress tensor and strain tensor. And here we have the elasticity matrix. So this, since this is a rank 4 matrix, we have 81 elastic constants, and we can write it as a 9 into 9 matrix. Among these constants, if we look at symmetry, conditions of symmetry due to symmetric matrices, then there is also energy relationship involved. So if we consider all of them, we have, I think most of these things I'm telling are what sir has already told. So I'll quickly go through. If you have doubts, you let me know. So if we remove those things, all those symmetry conditions, you will have only 21 left for an isotropic material, and for isotropic some other things come up, so you end up with only two elastic constants which are independent. So that was all in the two lectures of week 6. If there is anything else you want me to go through, you can let me know. Else we can maybe look at the assignments, or I have some more questions which are from previous year's assignments. So those also, if we have time, we can look through.
Sir, I have some doubts. Yes. This
Okay.
just sir, while speaking about a tensor of rank 4, in previous week clarification sessions, we had been told like if it is tensor of rank 0, it is stating like it is shows only scalar quantity. And a tensor of
Right.
rank 2, matlab it is showing scalar plus direction. And the tensor of
Yeah, yeah.
rank 2 means it is showing scalar plus direction with respect to plane. And what does
With
this rank
respect
4
to
tensor
planes.
actually represents?
Uh, so it's a good question. How you can better intuitively understand what it means. Mm, but actually, I myself am not aware of how exactly to understand it. What I know is that it relates to tensors of rank 2. That's why it's called of rank 4. I think it's better if you ask Archita this question tomorrow, because she deals with tensors a lot. She works mostly on computational things. So just mark it and ask her there. In case you feel your doubts are not getting resolved, you can post in the forum. I'll just see if there is something in the forum that I'm not seeing. Yeah. Actually, I forgot to see the forum this week. Couldn't- but what is your experience? You feel the forum is being like your doubts in forum are getting resolved, or you feel we should put more attention on it? You can
Sir,
let me
basically, yeah, I will let you know. Sir.
you can let me know. So we'll also accordingly try to pay more attention to it. Okay, so there are some questions I had not seen.
Yeah, sir, sir actually told that what is it? I forgot what is K. The K got infinity. There is something related to plasticity of the material.
Hmm, hmm, hmm.
Bulk what is that?
Hmm, hmm, hmm. I think sir told that if K becomes infinity, then the material will be incompressible. I'll just open that portion. So, it was here. Yeah. Mhm. So, you understand, no, that all these elastic constants like E, K, G, mu, they are telling you some of the properties, elastic properties of your material. For example, K will, you understand what K is telling you?
K, I understood K is something called bulk modulus.
Hmm.
That's it.
Hmm.
And
But,
K is infinitely proportional to compressibility.
hmm. So bulk modulus tells you about the compressibility. You are right. But you can maybe intuitively understand it as if you apply stress to your material, then how it will lead to a volume change in your material. I told no, it is K is given by maybe it's up here also, sigma by delta V by V. Yeah, so just like maybe you can understand shear elastic modulus as if you are putting some uniaxial stress, how the strain is getting affected, right? So this is also similar, just here you are looking at the volumetric strain instead of the maybe axial strain. So this is your volumetric strain, and K here is given, K is defined as sigma by delta. So now if we have, now that we know K and we have this relationship, so these these relationship come by some constitutive relations only. Constitutive relations, you have some idea what is a constitutive relation?
I understood that it is a stress strain relation. That's right.
Hmm. Yeah, it's a stress strain relation, but this is kind of a man-made relation. There is no that's what my understanding is. There is no way of just proving that this is what is the relation that is actually there. This is the man-made relation to be able to deal with all, to use mathematics to understand how stresses and strains are connected. So some mathematics that we ourselves constructed. So the most basic of it is saying that there is a Poisson ratio which connects your strains in one direction to the strains in another direction. So if you continue with those relations, then you will get these kinds of expressions. For example, the one which is connecting E and mu with K, right? And we know that any material which, if compressed, will have some, let's say, reduction in volume, but it cannot increase in volume, right? So K cannot be negative,
Mm.
right? If it is very hard, then it will not compress at all. You can call it incompressible. It's a extreme case. So if mu is equal to 0.5, that will correspond to K being infinity, which means that there is no strain, volumetric strain, even if you apply load. And that is the extreme case. You cannot have a K that is negative. That is the reason why Sir said that mu cannot be more than 0.5.
Sir, is it like if K
It's a
becomes
hmm.
infinite? the volumetric strain reaches to zero, then the material had got into plasticity.
K becomes infinite and volumetric strain becomes zero.
Then the material got into plasticity.
Then the material, okay. Mm, you can say that. Mm, but the thing is, you can say that mu equal to 0.5 corresponds to plastic deformation. But the reason we actually, if in your question also there something that you'll have to understand. So it's a very good question. I'll just maybe show it here. So when we are thinking about how plasticity, how the value of K will change during plasticity, uh, how can I let's slide over the question. Let's here. Yeah. Hmm. So we have seen that plasticity involves mu equal to 0.5
Generally, or
because generally always it will involve mu equal to 0.5. At least for metal alloys, I am aware. For other materials, also it should hold. And now you have asked whether having incompressible material will also mean that you are having plasticity. The deformation is plastic, right? Mm, so I think one way to approach this question that you have raised is that if you have let's just consider a simple case of elastic deformation. For example, you have some kind of a spherical material. You are loading it in a hydrostatic manner. So you only have normal stresses, and then you are seeing some deformation, and using that you are calculating the value of K equal to sigma by del. Okay, so this is the classic definition of K, or how K is explained. But now in case this was considering only elasticity. So if you are having some value of K, then it is only for the elastic deformation that occurred. Okay. But now if you want to consider plasticity, then in that case, let's say that you have some plastic deformation occurring. For example, in case of your tensile specimen, it plastically deformed to some extent. Then here what happened was plastic flow of material took place. So in a way, there was some bond switching that took place, due to which the material elongated. But I wouldn't think that it is uh, wise to associate a bulk modulus with plastic flow, because all of these constants, these have been derived for linear elastic conditions, right? And all the interrelationships also. So this, even the matrix that you saw elastic matrix, those are for application which involves elastic deformation, so that you can relate between different stresses and strain that are acting. But when you have plastic flow taking place, in that case, I think the just definition of bulk modulus will not hold, or at least these relationships we have, those will not hold. So it might not be uh, correct to just say that because you during plastic flow you do not have a change in volume, the bulk modulus is infinity, because there the definition of bulk modulus will not hold, or at least the relationship that we saw, E upon 2 into E upon something into 1 minus 2 mu, that will not hold. So definitely we can say that you cannot say that it's incompressible if it's plastic. It's a very good question. I had not thought of it before. I hope it was clear. If you have any further confusion, you can ask.
My understanding, how I understood is like we derived this equation assuming that the change is linear and it is an isotropic material. So
Hmm.
applying the plastic Poisson's ratio and quoting some relation between plasticity in this equation, which had been derived for elastic conditions, is not acceptable.
Yeah. Yeah, you are right. Also, another thing I'll like to clarify. Uh, so when we say that a plastic material has a mu of 0.5, the way I said here, it's not a very so here I am not being true to the assumptions that we are making of linear elastic deformation,
Okay.
right? Because we have
Okay.
started with that assumption, right? And based on that, we have built up all of these concepts of elastic constants, their relationships. But here, when we are trying to calculate mu for plastic deformation, then in that case, we are just seeing how your minus epsilon xx by epsilon yy will change, or what will be the value of this expression when you are plastically deforming your material, right? Because this is how we defined the value of mu. But in this case, we are not looking at elastic strains, we are looking at plastic strains, right? And somehow it will come out that because there is no volume change due to the reasoning I gave, the physical reasoning, it will come out that mu will be equal to 0.5. But this value is you cannot directly compare this to what you are getting during elastic deformation of a material. So material which is elastically deforming and giving you 0.5 is behaving actually differently from one which is plastically deforming and giving you mu 0.5. So this is not a apple to apple comparison. You can consider this as a apple to orange comparison. For example, in that slide also, if we see, uh, where is it? New window. There also there is an example of cork given, right? Which is often put in champagne or some liquor bottles. And sir
Yeah.
explained in his video why it was chosen to put in that those bottles. So there the deformation that happens is when you are compressing it into your bottle is a elastic deformation, right? And even for that deformation, it gives you mu of 0.5. But any other material will not give you that. A metal will not give you that. When it plastically deforms, based on how we are defining mu, the expression of mu, you will get zero point 0.5 value. But that behavior is different from what it happens for a elastically deforming material. So that discernment you will have to have when you are saying, sir did not explain this in detail. He just went over this. But that is something you will have to understand if you want to compare between the mu values. If you have any question, confusion, you can let me know.
Yes, sir, I understand. Like mu point 0.5 in elasticity is not equal to mu point 0.5 in plasticity. So there are something else is also taking place in plasticity. Actually.
Hmm. Basically, in short, yeah, if you have confusion, you can tell me, then I can explain better.
Sir, this doubt is clarified.
This, so a simple way of understanding this is just looking at cork, which elastically deforms with mu equal to zero point 0.5, and any other metal or other material, which will plastically deform as zero point 0.5. So all materials will deform plastically with mu of zero point 0.5, but then you have to have that discernment that it is not elastic strains that are being seen when calculating mu there. So you cannot use that value of mu in calculating those other constants also, because that all these relationships will break down under plastic deformation. Yeah. Okay. So if this is resolved, then any
And
other
sir,
thing?
there is some doubt in Boschinger's effect.
Washington's effect. Huh. Yeah. Yeah. Okay. And which lecture was it in? The second one.
It's lecture. Yes, second one. Yes. 18.
This is, I think, this one.
After is Lamb is constant.
Hmm. Okay. Lambda.
After Lamb is constant.
Lamb's constant. Yeah. So. Hmm. Hmm. So here, sir has told that if you are deforming by tension, then again loading it in opposite direction in compression, then reloading it, then in that case, the response you get will not be exactly the same. It will, there will be a reduction in the stresses that are required to get the same value of strain as earlier. So maybe I can show it here as this. Um, Actually, this is not very accurate. Let's just. Is there something particular that you have a doubt in this?
Yes, sir. So this epsilon.
Mhm. So actually, here I think there is a small mistake in this lecture. I also noticed it earlier. So here, sir says that there is a change in the Young's modulus, right? When you are loading and unloading, and then reloading in opposite direction.
Mm,
And this is here called Boschinger's effect. But actually, even if you see in this plot, the second one, what you will see is that the slopes are all the same during loading, unloading, or reloading, right?
mm,
So Young's modulus does not change if in this kind of a situation, since Young's modulus is a very fundamental quantity. It's associated with the strength of a bond when it is stretched or compressed. So it is not affected if you will load and unload a material. What is actually affected is the strength that the material will show. So this is actually a kind of loading which is called fatigue. And this kind of plot will only come
cyclic plot.
when you take it towards when there is some plastic deformation taking place in your material, which is understandable, right? When you relax your material, you have some residual strains.
Stream.
So these are nothing but the plastic strains which were accumulated when you were applying stresses. So the thing is that what Boschinger's effect actually tells you is that if you are compressing a material, then it's easier to deform the material by repeated tension and compression rather than just applying tension due to some uh, internal processes that take place, dislocation associated processes, due to which the material will become, can be, you can understand it as material is much more weaker when you apply repeating tension and compression rather than just applying tension. So because of this phenomena only, even if your stress which you are applying is much lower than your tensile strength, still you can break a material just by repeatedly loading and unloading it. Hmm. It makes sense. If you have any doubt, you can let me know. We have, I think, enough time. So if anything in particular you couldn't
Sir,
understand.
actually, I was about to ask, like, if we are applying positive stress, we are seeing
Hmm.
the Young's modulus with respect to positive strain.
With respect to positive strain, yes, yeah.
So, if we are seeing with respect to negative stress, that's the downward of y-axis, so we have to consider with respect to negative strain only. No? If we are
Yes.
going to see Young's modulus, then why it is compared, like why be in like fourth quadrant, meaning stating negative stress and positive strain. Will it be a right comparison?
You are saying
YB
this
is in
quadrant, fourth quadrant.
fourth
Okay.
quadrant, but it should be in third no? Because we are seeing for something like a
Hmm.
negative stresses. It should be negative strain, then we will be getting the E. So if we see that the E is actually remaining same, oh,
Hmm.
sorry, Young's modulus is actually remaining same. So any specific reasons like why this kind of comparison is being made?
I see. So maybe I can just explain this loading to you, then it will be a bit clear. Yeah. Uh, let's say you have also when you are saying Young's modulus, let's say E, then what you're looking at is sigma by
Yes.
epsilon, let's say xx, in the direction with which you can call it sigma xx also. If you have a unidirectional loading, then how is the strain along that same direction changing? So initially you have this kind of a load, right? Some plastic deformation also occurred, and now you are reversing it.
Mm,
So it will relax like this, but then you
mm,
are also taking it to applying compressive loads on it.
mm,
So for example, in case of bridges, anything that experiences fatigue, for example, the axles of a wheel or bridges or aeroplanes which are flying. Uh, so when they're flying, there is air coming from the forces. Since you are more interested in aircraft, there are different forces that will experience. hydro, what should I, what is called? Mm, some, so we call it, some lift forces are there which it experiences, right? And then some other forces due to the speed at which it is going, maybe frictional kind of forces. And when it is going up and down, like it's landing, then it's again taking off. All of these are repeated loading cycles, right? So this is a very common phenomena which materials experience. So if you are then applying a compressive load, then since it has already deformed plastically, it will have some strain, plastic strain. And now when you are deforming, like applying more compressive loads, it will continue from here. So strains are actually decreasing, but still it's a positive strain. You will have to apply some loads to bring the strain to zero, then it will become negative. And now if you again start reducing your load, it will again elastically deform, like elastically relax. It will come and stop at some negative value of strain. And now it will enter your second quadrant where your strain is negative, stress is positive, and slowly it will again go back here. So this is if you do not have Boschinger's effect, then you'll have this kind of a cycle. But then due to some internal processes that are occurring in the material, for example, I'll tell you for a constant strain loading, since some of my lab mates work on fatty. So what they observe is that if have a constant strain at which you are loading and unloading, let's say epsilon value minus epsilon, then instead of this happening, so normally you expect that the material will keep strain hardening as it is plastically deformed, right? The plastic strains will
till
accumulate,
till UTS.
right? Sorry,
Till UTS.
till UTS. So plastic strains will keep accumulating and that will strain harden the material. The material will become stronger. But what we see is that due to Boschinger's effect, the material does not become as strong as we anticipated. So maybe it will go up. So more stresses are required to strain the material. So slightly it will keep on going up, something like this. But after a point, it will start to some defect will originate, which is big enough to make a crack propagate. And there it will fail. So it might be this value, which will be much less than UTS. Let's say this is
Okay.
sigma. And this can be a very small strain. It could be maybe around 0.5%, 0.5% of strain, a constant strain at which we are loading and unloading. And even that, due to this effect, will lead to failure.
Okay, so this change in stress strain graph for this material is happening because it is previously loaded.
The change in the stress strain graph.
Curve
So,
is
do
happening because
you
of the residual strain which is actually present.
Yeah, due to the question which you had earlier posed about the fourth quadrant. So it's due to
Yes,
residual
yes.
strain.
Means
But
recently now I got.
when you are measuring yeah, Young's modulus, you need not consider what is the plastic deformation that is in the material, because you are so this thing you can I think you should try to make clear that any elastic deformation means stretching of bonds only. So there is nothing else happening other than bonds. So every atom is attached to multiple other atoms based on how its structure is. And when you are elastically deforming, some bonds are getting elongated, stretched, some are getting compressed, again due to Poisson's ratio. And so that should not be affected by how the plastic deformation has occurred or what is the plastic deformation in that material. So even if here you measure the slope of this, you will get the same Young's modulus value, no matter whether it's while giving tensile load or compressive load, it will be the same.
Sir, actually, it is like when we are applying load, tensile load, we are measuring Young's modulus in positive strain.
Okay, okay.
We are removing load and it is coming to negative stress axis, and then
Hmm.
we are continuously adding compression, so it is going to negative strain and negative stress. So if we want to measure Young's modulus, we have to measure there only.
If you want to measure Young's modulus during your negative stress and strain regime, you are
Ah,
saying?
ah. Then only we can compare and tell whether something had happened due to the residual strain or not.
Let's say you like, as a researcher or as a curious person, you want to know whether Young's modulus is changing when you are loading, like giving tensile load or giving compressive load when there is already some residual strain. You can do that measurement, right? So
Hmm.
if you do that kind of a measurement, what you will be doing is, so one way is that you start with a normal unloaded material. You give it some load,
Hmm.
and assuming you have a very accurate calibrated strain gauge and load cell, you can get accurate values of stress and strain. And based on this deformation, you calculated some Young's modulus. Okay. Now you went till some value of strain, then you relaxed it. You could see how the stress is reduced as it is relaxed. And based on these values, you again got another value of Young's modulus based on the slope only, right? And once it is at zero stress, there is some deformation that is still there, plastic deformation, but now you decide to give compressive stresses, right? So now you decided to apply stress in the opposite direction, and you kept on loading it until you went till until you got a certain amount of strain. Then you decided to unload it. So during this compressive loading also you can measure some value of Young's modulus Ym. So you can get one, two, three different values.
Four.
And now during compressive unloading also you'll get some value. So you can make these measurements,
Okay.
and then again this cycle will repeat. So these you can make, and what it has been found is that all of these slopes will always come out to be parallel, right? Considering some error which is due to larger displacements are that the material is being subjected to, and also due to some error due to your measurement technique, there will be some error, but largely all these values come out to be the same.
Like any specific reason for comparing of 1 and 3 rather than 1 and 4?
1 and 3
Huh.
rather than 1 and 4. Mm, no reason actually. Actually, there is no need to compare the Young's modulus. This was a mistake, as I told no in the lecture, that the Young's modulus will change on compression or tension. That does not happen. So actually, you need not even compare it. What you need to focus on is the effect of plastic deformation and the effect of compressive repeated loading on the stresses and strains that you are getting, the response that the material is giving. So that is more important. So what normally in if you are studying the plastic deformation during fatigue, what you will be interested in is how my material is responding to the plastic to the repeated loading. So what are the value of stresses and strains that I am getting after maybe first cycle or the first 100 cycle, 1000 cycles, 2000 cycles. So usually what we see, if you want to look at more detail, sir has not covered this. He just covered this for maybe a minute or so. But if you look at the number of cycles, because I have some lab mates working on this thing, so I know how they analyze their results. So if you are just curious, I can show you. If you have, let's say, number of cycles here and the sigma max we call it, or sigma peak we call it, the peak stress during a cycle. So like I showed now, you can have multiple cycles. During every cycle, there is a peak stress in which you get at which you get the desired stream. Then you again compress it and take it in the other direction. So what is usually observed is that it will start somewhere here, maybe at zeroth cycle it will be somewhere here. It will increase a bit. It it's not linear increase, but it increases a bit based on the internal processes. Then it tends to saturate. Then because some change in processes, change in the structure and the material takes place, at least in alloy, you will have some. So we call this hardening of material. We call this softening process. And slowly, after a point, it will some crack generation will take place, and then it will go down much more quickly. So this is what we are interested in, how the peak stresses or the if you are doing a strain control one, if you are doing stress control, then how the strain response is changing over time. So I think for now you should just maybe correct yourself and others also who might see this video later on that young modelers will not be changing. Maybe I'll inform sir also once later on that this is the case.
Sir, can I get any gist regarding that ASTM D3039? Some gist points, just to hear what it is actually stated.
Okay. I see. Give me a minute. I'll just note that down this. Leg 18, uh, page 20, mistake. Sir also sometimes asks us to just report if there is some error which might be there. Okay.
Sir,
You were
can
asking
we
about
get some
ASTM.
updates regarding if Sir told something to change or rectify it? Can we get some updations regarding that and discussion points?
Uh,
If
uh,
Sir said that he's going to change this because of certain stuffs, so can we get? If you come to know, can we get that information in discussion forums?
I did not actually get what change in what are
So,
you are
so if the sir actually
mentioning.
tells that the content of the course is getting changed a little bit due to some other reasons, so if you got to know those stuffs, can we get to know that in discussion
Okay.
forums?
Sir has told it in his video lecture.
No, no. If you get to know that sir is gonna change something, like
Okay.
what is it you're gonna report to sir, and if sir considers this and try to change, can we hear
Okay.
that in
In
discussion
case
forum?
we get to know, but actually, sir is like, frankly, sir is also quite busy. I am sure he'll note down the mistakes. For example, in assignments, Archita also told that there were some questions which were not having the correct answers. So those things we just report to sir's student who takes care of this. But I don't think this course will be revised in like come
Not
at least
course,
for
just some
some time.
contents. Okay.
I'm not sure if it will be revised. Maybe the assignments might be corrected because changing the video lectures is very difficult, right?
Hmm.
Later on, maybe if uh, sir feels that now it's time to update it, he might do it. For now, I think this is quite error if we compare to most courses that are out there. This is very well made and like everything is quite uh, all facts are right, I feel. And even sir explains from bottom up, so understanding wise also everything is good in this, I feel. I'll let you know in case there's something like this.
Mm.
Elastic constants. Anything else that you want
Uh,
to
some just regarding that ASTM
ask?
D3039,
Okay, I think it was the
something to
previous.
understand at least.
Hmm.
Sir told like
This is
that
for
would
the
be
poisons ratio measurement,
for if
right?
we are keeping two strain gauges.
Hmm. Okay. Which slide is it? It's not here. ASTM atoms. Hmm. So this explains what are the precautions that you have to take when you use two stones and not this. Hmm. Actually, I am also not aware. I'll have to. Have you ever seen any ASTM? They have
Sir,
kind
like
of
less audible.
some short notes that they have. They are kind of papers only, but there it's more about explanation of a procedure of how you can measure something and what are the standards associated with that measurement. Maybe you can just look up on web. You'll be able to download that particular guideline, and if you have time, if you want to know, you can just try to see. And then if you have any doubt, maybe just post in forum with the associated content that you have a doubt in. You can put images or something. Then I have seen this Mr. Ramesh, who is her student actually. He used to be the TA earlier for this course, so he has answered some of these questions because I think he answers with much more deeper understanding, I guess, than those like me and Archita who are newer to this course. So it's good. I think you can keep posting there. It's good. T3039. And frankly, what I'll say from my experience is that the depth of understanding you're getting in this course, there are very few courses from which you'll and be able to understand this much. So sir has been explaining things from various perspectives. From the very basic things, he has been building up different concepts. So it's good that you are following it thoroughly. Anything else you want me to look at? Or we can look at the assignment
Yes,
questions directly.
yes, sir. So the doubts for this week is done actually.
Okay, good.
And I have some doubts regarding previous week's assignment. Some of my answers got wrong. So
Okay, okay. Maybe you can, okay, ask here also.
regarding that stress strain curve, sir. So
Should I open that assignment
just
last week's?
one thing.
Okay.
So the stress strain curve for a MS general MS stress strain curve.
Uh, okay. From the
In that we
assignment
will
you're saying, or
label
just
yes,
you have
yes,
some
yes,
doubt?
yes from the assignment.
Uh,
So there we will be labeling something like a proportionality limit, elastic limit, and high yield strength, lower yield point, UTS, and fracture rate. Sir, am I audible?
Hello. Sorry, I think some connection issue was there. Hmm.
So in the stress strain curve for
Now,
a mild steel specimen,
okay.
we will be having some proportionality limit, elastic limit, higher yield
Hmm.
point, lower yield point, UTS, and fracture rate.
Okay. Okay.
So proportionality limit is still where the Hooke's law is valid. So the slope will be linear now.
Till where the hoop law is lam valid. Yes. Till there it should be
Ah,
linear.
then
Hmm.
till elastic limit, there should be a slope with a slight change in a curve pattern. Correct, correct, sir?
Mm,
Or
yeah.
no?
Elastic limit. There should be some. There can be some slope because there we are concerned with only elasticity, not with the proportionality. Okay. Hmm.
So then here B becomes the right answer now because till A
Okay.
the slope is perfectly linear.
I see. Yeah, yeah, yeah. I see.
So I thought A should be the proportionality limit. I thought B should be the elastic
Elastic limit.
limit, and the C is lower yield point. So I
Hmm.
considered A, and it got wrong.
Okay, I see. Actually, for mild steel, uh, so they are saying A is the answer. Okay. So, like my understanding of it, the reason why I had told the answer should be A is because uh, what happens in mild steel or similar steels, where you see this kind of phenomena. This is, I think, called mm, yield point phenomena, or we also call it quadrille atmosphere, like those who study metallurgy or materials engineering. So we are aware of this kind of thing. So this is called the theory of this is called quadrille atmosphere. The reason we have a lowering or a dip in the stress strain curve, followed by again increase. And I think this is called the yield point phenomena also. So what happens here is that okay, initially you have a kind of a linear slope. So we can call it just elastic deformation. And then you will have, if I just zoom this thing up, it will be like this, but then it will show slight plastic deformation. Like some plasticity will take place in the material theoretically. And after that, due to certain reasons, due to actually, I don't want to get into the details, but what happens based on theory is that there are certain solute atoms in your, let's say, milestone, which are actually restricting the movement of some dislocations. And because of that, plastic deformation becomes difficult. So you will see a increase in your stress response because more stress is required to make your material flow or cause strain. But then due to your stress reaching a certain value, those dislocations break away from your solute atom, and since they are able to break away, now lesser stresses are required to keep them mobile or keep them moving. So there is a slight dip, and after that there are enough number of dislocation structures to keep this moving. So that is like the technical reason for it. Probably you will not be able to understand because this is new for you. But what happens is that just here itself, where you had some plastic deformation starting, some change in slope, you will start. So you can consider this itself as the yield point. And after this, you have plastic deformation, some lowering due to internal processes that are taking place in your mild steel, due to the composition and atoms which are present in your material. And then again, it will keep increasing the way it is normally for any alloy, strain hardening. So because of this, you can consider this as your proportionality limit also, as well as maybe elastic limit. So these are actually proportionality limit or elastic limit. These are not very scientific terms. These are more for just application point of view, because they can vary be here and there based on your material, or even for same material different specimens, they can vary a little bit here and there. There is no very scientific way of defining them. So considering that, I think you can just consider A to be where elasticity, where plasticity will start. So that's why you can call this elastic limit.
Then where is proportionality limits?
Proportionality limit, I think you can just call A only as the proportionality limit also. Mm, from what I think, mm, yeah, you can just call A also as the proportionality limit. If this was, I know you might have studied somewhere or read online also, that you explained it, right? That initially the linear region you can consider as the elastic one. At the end, you'll have the elastic limit. Then you have little bit more of elastic deformation, which is not linear. So you, sorry, this will be the proportionality limit. Then
Hmm.
the next one will be the elastic limit. After that, you will have your plastic deformation. Usually, I think that is how they explain it. It will not be like this, maybe like this, right? So this is your elastic limit, proportionality limit, and yielding will also, I think, be here only.
Somewhere.
I'm not sure. Somewhere after the elastic limit or at the elastic limit, then you will have the plastic deformation starting. But these are just some terminologies that we use. Like here, as I said, no, these elastic limit or plastic or proportionality limit, these are just some terminologies to make our understanding simple from application point of view. These are not very scientific terms actually. But for this question, I think maybe if you still have maybe Ganesh, who is a student, he can also give his opinion on it. You can just post it in the discussion forum if you still are doubtful, and maybe he can give his view whether A should be the correct answer or not. Mhm. What I'd suggest, just take a snapshot of this and put it in the discussion forum, and just tell that this is belonging to this particular week's assignment, and then maybe he can give you his opinion. I feel for now A should be okay.
B should also be okay.
Hmm. B. So as I told, no, in case of mild steel, you have this kind of behavior. Uh, so professor did not explain this, but you have this kind of thing where you have plastic deformation till some peak stress, then there will be a loading,
Yes.
and then again it will increase. So this is also considered plastic, at least for mild steel. So that's why I said that it should be a. In case of confusion, you can post and see
And
if
said that
what like.
whole
Sorry,
and that wholesome process,
whole field
wholesome
measurement, no?
process, whole field measurement.
What is the answer to
I
this?
said actually it is like a DIC only, but why not photoelastic? Because they didn't specifically mention that, like it should be done
Photo.
throughout the stuff or till yielding. They didn't mention it. No. So someone
So
could
I
have
think.
even think like we are
Mhm.
making it for a ductile material. So ductile material yielding should not happen. So till yielding only we are going to measure and applying photoelasticity should work.
Ductile material yielding should not happen, you see.
Till yielding only we are going to measure for ductile material, which is
Hmm,
actually
hmm, hmm.
applied in some fields.
Hmm, hmm,
Like we can take landing gears. So why not
hmm, hmm.
photoelasticity? Because DIC will not work here.
Oh, yeah, I see. So actually, the reason I told digital image correlation. So here also it's um, wait a minute. This my pen is not working. Anyways, okay. So the reason I told digital image correlation was because firstly, it just asking what is the best suited technique for measurement of strain, right? So both are whole field. That is true. What you mentioned that at least, especially in the elastic part, both of these will give you whole field measurement. But can you tell me what will be the drawbacks of using photoelasticity if I want to
We
measure
cannot use it
strain?
in plastic.
One thing is you can't use it in plastic resin. Yeah. Anything else that might be there?
We can measure stresses in photoelasticity.
Yeah. So what you'll be getting will be the stress values. In DIC, you will get the displacements.
Hmm.
So there the calculation of strain is much more straightforward. In photoelasticity, you will have to convert your stresses to strain based on the moduli values, which you already know, right? So that is another limitation. And anything else that might be there that you can think of?
Yes. I thought photoelasticity also should work.
Uh, so, so there is one more limitation I feel compared to DIC for photoelasticity. Can you think of anything? Maybe you also can come up with something. Hmm. So one limitation can be photoelasticity can give you the stress values at all points, but it will only tell you what is the value of stresses along the principal directions, right? It will give you stress contours. It will not tell you, like if you want to look at these details, it will not tell you how the stresses will be in different directions. But in case of DIC, you are measuring the displacements of different points. So you can use those to get the strain values in any direction, right? So this information you cannot get from photoelasticity. So because of these reasons, it's much more convenient also, and you are getting more information when you are using DIC for strain measurement compared to photoelasticity. So from a more experimental point of view, practical point of view, I'll say DIC is a much more, because we do DIC, we have never done photoelasticity. So it's a much more uh, practical route of measurement. Photoelasticity, of course, will have its strengths in particular applications or for better understanding of the stresses. The stresses are much more difficult to intuitively understand or measure also compared to strains. Okay. Anything else?
Thanks.
Okay, that's all, no? So should we look at the week 6 question? There are not many questions here. It has fewer
There are
questions
questions
for
that's
some
getting
reason.
easier.
So quickly, I think you can answer all of these very easily. You have gone through the lectures. Can you just tell me what you think the answers will be?
A number of independent elastic constants applied to anisotropic material are at least 21.
21, yeah, that's the answer.
If a material experiences no change in volume when subjected to stress. No change in volume. Okay. Subjected to stress. Is point point five. Point five.
Point 5, yeah.
What must become infinity.
Yeah, yes.
What is the ratio of inch modulus to shear modulus of an elastic material in terms of Poisson's ratio? G equals to E by 2 of 1 minus mu. Ah, A. 2 of 1 minus mu.
2 and 2. Is this the expression? I think
Ah,
it's 1 plus
G
mu.
equals
Can you
to
check?
E by oh, 1 plus mu.
Can you just check once?
1 plus mu.
1 plus mu, right?
Ah,
Okay. Yeah. Mm-hmm.
the figure shows the stress strain behavior of different materials. Answer the following question. Enter the corresponding alphabets A, B, C, D as answers. Strain hardening, perfect. Okay.
Hmm. So let's see. Look at the. So we have to tell for rigid material, elastic, perfect elastic material, which of the points these will correspond to. Yeah.
5 will be A and 6 will be D.
6 will be B,
D,
elastic,
D, D,
perfectly
D,
placid. D.
D,
Okay,
D.
D. You're saying fifth will be
Uh,
B.
Fifth will be
Rig
A.
A. Rigid material will be A. Okay. Okay. A and D.
What
Yeah.
is the Poisson's
This
ratio
is
of
a
for a bulk to
correct
different
answer,
material?
I
Is the
guess. Yeah.
modulus of rigidity equal to bulk modulus? Just a minute. Um, is to be sir, will it be like minus 1 by 8? Is it right?
Minus 1 by 8.
Right?
Uh, you're saying minus 1 by 8.
Huh. Is it correct?
Actually, I myself have not calculated yet. Can you just tell what is the reasoning or what is the steps you followed?
Basically, equating the equations g equals to e divided by 2 of 1 plus nu and
And
k equals to
K is,
e by 3 1 minus 2 nu.
yeah, 1 minus 2 mu. So you
So
can equate
equating
these
these
two.
two, e will get cancelled. So 3
Hmm.
minus 6 nu will be equal to 2 plus 2 nu. So
Okay.
I will be getting minus 8 nu. My oh shit, I did something wrong. It's actually plus 1 by 8.
Yeah, it will be plus 1 by 8. Okay. So this way you can say it's plus 1 by 8. Okay.
Likewise, I got 6 marks gone because of sign conventions.
Yeah. In the previous assignment.
Yeah, every answers are correct, but by typing, I made it as minus.
Okay,
So
okay. I see.
6 marks gone.
I think the end term has much more weightage for this course, right? Assignments also
Hmm?
must be important,
Uh,
but
so I will not do those mistakes. Future.
just do it more slowly. That way it's better.
Choose the correct statements. In isotropic materials, shear stress corresponds to development of shear strength. Yes. Uh,
Okay.
in isotropic materials, shear component corresponds to shear strength as well as normal strength. No. In isotropic material, pure shear load will produce distortion of the specimen through changes in angle between the adjacent sides which cause no changes in I didn't understand. The thermal stress occurs when expansion or contraction due to thermal effects. It's constraint. Wood is an orthotropic material. In isotropic material, a pure shear load will produce distortion of the specimen through change in angles between the adjacent sides, but will cause no change in lengths. Yes. 1, 2, 3. Sir, 1, 3, 4, 5 is right. 2 is wrong.
1, 3,
4, 5.
4, 5. Yeah. You are right. All of these will be correct. Okay. I think you understand why it is so. So
Hmm.
let's look at this. This is the last question.
Okay. Give me some time to make it.
Maybe just tell me the approach for this. Just read it and tell
Um,
the approach.
Young's modulus for calculate. Okay. Bar with 30 dia is there. Okay. Specific tensile force 50 kilonewton is observed that elongation over a gauge with gauge length is. Sir, I have a small doubt in this.
Okay.
Basically, an object with a rectangular cross section will be called as bar, right? With a circular cross section will be called as shaft.
Yeah, rectangular cross section is called as bar. I think like
Sorry,
if you are studying
square cross section.
square
Square cross
cross
section.
section is called bar.
No.
I think if you are studying structures, that is how the nomenclature is. Shaft is circular.
But
I am not
but
so aware of it. Uh, hmm. So here they have called in strength of
keeping this
materials.
as
Actually, you don't
the
have this
same.
kind of.
Okay, okay, fine, fine. We can easily find out the area and the force just by dividing them. You will be getting we will be getting stress, and stress by the strain, like del L by L.
Hmm.
Zero point 0.2 by
Hmm.
200 we will be getting strain. So stress by strain we will be getting Young's modulus, and Poisson's ratio will be hmm, yeah, we are
Yeah.
having diameter and reduction in diameter, and the length plus increase in length. So by sigma epsilon xx by epsilon yy, we will be getting Poisson's ratio between minus
Epsilon xx by
epsilon
epsilon
yy.
y. The negative. But if you are
It,
considering the signs also, then it's positive. Okay. But yeah, you will have to negative.
it will be in reduction.
Hmm. Yeah. Now for 11th and 12th.
To determine the value of modulus of rigidity. Modulus of rigidity, we can make it using E by 1 plus E by 2 of 1 plus E.
Okay.
So it's the same for bulk modulus, E by 3 of 1 minus 2.
Yes. Mhm. Okay. That's all for the assignments for this content. For thermal strains, you have some more questions. Maybe two or three other questions, I
Thermostat
guess.
is hopefully done.
Uh,
Last question is one on pending, sir. Calculation parts. A bit
okay.
confused regarding that mechanics.
Okay. Yeah. Fine. So I think we can close the session now.
Sir, one small request.
Hmm.
Sir is telling something additional information. So can we get them in discussion forums like available for everyone?
No, I didn't get you. Additional information?
Like sir is telling something called standards, ASTM 3036,
Ha,
like
ha,
that,
ha.
and it is also stating something called tempering of classes, and
Okay. Yeah, yeah.
uh, he's quoting another example called something negative Poisson ratio
Negative Poisson's ratio. Yeah.
for some stem cells plantations being
Hmm.
used in using
Stent.
some
Yeah, yeah.
materials, oxytones, oxones, something like that. So, can we get some information regarding that oxatics material? So, NPR polyurethane foam. He said
Some
it is like
polymers.
points
Hmm.
minus points. So, some information regarding
Hmm. Some information regarding that.
additional information.
So one thing you asked was tempering of glass, then the
Mm, mm.
negative Poisson's ratio materials, those used in stents, and ASTM related things. No?
Ah, ah, mm.
Hmm. Uh, I've told you like for ASTM you'll have to refer online. For this also negative Poisson's ratio, if you find it interesting, you are more curious because if you have some doubts in concepts, then of course the discussion forum is for that only. But for these also you can post it if you want, like no need to hesitate too much. But I think for these specific details, no specific extra information you want, you can just go to web and try to look at it. Maybe use some AI tools also, chat GPT and those things, to it can give you much larger amount of information. And then you can look for different sites also. For example, for this negative Poisson's ratio, you can try to look at it from multiple points of view, like how the atomic structures or the components of the atomic components are leading to this kind of effect, or how you can tailor this effect for different applications, for example in stents. So it's an interesting thing. I'll suggest you just look it online. I'll also not be able to tell you much. It's new for me also. I've never explored it much. Hmm.
Thanks.
Well, that's okay. But do not hesitate to put in the discussion forum, because other students also, I think, benefit a lot from looking at it. Hmm. Okay. Hmm. Okay. Also, I wanted to just speak to you for a few minutes since we talked once before. So I'll first just stop this recording. Yeah. Okay.